All right, welcome back, guys. I'm going to start from page 156, and we're continuing our unit on exponential growth by talking about compound interest. Okay, so in general, everyone knows what interest is. Basically, money in your bank grows, or if you borrow money, you're going to owe more money at the end of it than you did when you borrowed it. Okay, and so it's usually calculated as a percentage of what you borrowed or what you have given. Okay, so if you read our little paragraph here, we talk about whether you borrowed money or whether you have been given money. And we mentioned something called simple interest, which is basically you just multiply the percentage on your dollar, right? But the real way everything works is compound interest, where the money that grows actually grows based on the interest you've actually earned already. So every so often your interest gets added in to the amount that you've invested. Okay, and the amount that you've invested, we typically refer to that as the principal. Okay, now up at the top, you'll see the formula for how we calculate compound interest up here. And some of the variables that you see, A, P, R, N, and T, right? So those are all representing different factors that are involved. So P stands for the principal, and that's really just the starting amount. Then we have R, which is your interest rate, which is as a decimal, okay? So it's a percentage, but we're going to use it as a decimal, okay? And by that I mean 5% would be 0.05 as a decimal, okay? Now N represents our compounding period, okay? And that just means how often do you check your money? Are you checking it every day for the interest growth? Are you checking it every year? Are you checking it every month? Every other month? So on and so forth. And then finally, the last variable we have is t, which is your time. And in general, we're just going to be measuring that in years, unless there's something special going on. Okay, so we know the principal, that's your starting amount, the rate, which is your percentage of growth as a decimal. Okay, we're going to talk about the compounding period, which is how often we actually check our growth, and the time, which we measure in years. Now, underneath those variables, we've listed out, hey, how often you're checking that n value and the different numbers we associate with it, right? So annually, n equals 1, once a year. Semi-annually, twice a year. Quarterly is 4 times a year. Monthly, or 12 months. Bi-monthly, so twice a month. This is going to be 24, okay? Weekly, 52 weeks in a year, and daily, 365 days in a year. Okay, now let me note, sometimes you'll hear some different terms, but usually it's good to think, how many times does this happen in a year? And you could theoretically break this up however you want. If you want to check your money 7 times a year, you can absolutely do that. It's just a little bit of a weird breakdown. Okay, so all we're going to have to do is we're going to kind of fill everything in this formula, and we'll be able to calculate our account balance, or the final amount, A, after this time has passed. Let's see an example. Okay, so here we go. We have an example. This is $800 is deposited in an account that pays 9% annual interest compounded annually. Find the balance after 4 years. Okay, so we're going to start by identifying what our variables are, and let's see how that goes. So $800 is deposited. That sounds like my starting amount, so I'm going to call that my P, $800. The account pays 9% annual interest, okay? So 9% per year, okay? And remember, we're always going to write that as a decimal. So it's 9%, but we never calculate like that. We're going to write 0.09, okay? And how often we're checking that compounding. If you refer back to the chart above, we mentioned compounding annually only once a year. So N is going to be 1. And finally, T, we said we're going to leave the money in the bank for 4 years. So T will be 4. Okay, let's take a second. Let's set up our formula for this. Okay, so I'm going to copy the formula down real quick. A equals P1 plus R over N raised to the N times T power. Okay, and now once I've got the equation, of course, we're just going to plug in all the numbers. So I'm solving for A, and we've got $800 starting 1 plus 0.09 over 1 times 4. And now once we've got this, we can kind of just calculate everything out. And we'll have to use a calculator, of course. We can't really do this by hand. We should get 1129.27. And I'm rounding to 2 decimal points because we're talking about money. So at the end of our 4 years, we've got $1,129.27 from that 8% that we started with, okay? So we did pretty well on our money there. Okay, let's try one more example, okay? Take a moment, go ahead and try to fill in these variables without looking at what my answer is, and then see how you did, okay? Hopefully you got that the 2250 is the initial amount that we started with, our principal, 6% rate at 0.06, n is 4 because we compound quarterly, and our balance we're looking for after 10 years, so time is going to be 10 years. Let's go ahead and fill everything into our equation. So again, A equals P1 plus R over N to the NT power. And we're just going to plug in the numbers that we know in here. So here we go, 2250 times 1 plus 0.06 over 4 to the 4 times 10 power, okay? And again, we can rely on our calculator to kind of help us with this. We can definitely, like, if you don't have a fancy calculator, we can definitely simplify inside the parentheses first and kind of work that out and then start doing the whole exponent and everything. So go ahead and type this in your calculator or whatever you're using to compute. I'll show you kind of if you had to use something that wasn't a really fancy calculator, you could do 2250 times this parentheses, you should get 1.015 to the 40 power. So you could definitely calculate out the exponent first and then multiply by 2250 after that. Okay, but if your calculator is at least a little bit reasonable, or if you're using one of these online ones, you should be able to get the answer for this without even taking that step. And your final answer should be $4,081.54. So that 2250 grew into $4,000. Okay, so question 3, or example, doesn't mention a bank this time. You have an emerald ring that has a appraised value, and we're now passing 50 years, and we're trying to see how much the value of your ring has increased. Okay, we'll set it up the exact same way. We're still going to use the same thing. All right, see if you can identify your variables. Remember, we need P, R, N, and T. Those are the 4 numbers we really need. And we're going to try and solve for A. Okay, so let's figure that out. So hopefully if you filled this in, you'll have $2,400 is the appraised value, my starting amount. My rate is 6%, so I'm going to say 0.06. And it's only going to count by year, right? It says each year and it doesn't mention any other compounding, so I'm going to go ahead and say that N is 1. And we started from 1960 and went till 2010. That is 50 years. All right, and I want to figure out my final value, how much this ring is worth. All right, now that we've identified all the variables, take a minute. You guys try to set up the formula, and then I'm going to do it with you as well. So pause and try to solve it yourself. And as you can see my setup for it, 2400 times 1 plus 0.06 over 1 times 50 in the exponent. And I came up with $44,208.37. So after 50 years, you can see that $2,400 ring is definitely worth a whole lot more. Okay, stepping back from our compound interest formula, I'm going to show you a different application for exponential growth and decay, and that is half-life. So half-life talks about elements that are radioactive or unstable, and they kind of break down and start to decay away. All right, so I'm going to go ahead and show you what the half-life formula is, and then we'll see if we can apply it to this problem. So the formula goes something like this. Your final amount is equal to the initial amount times 1/2 to the time divided by the half-life. Okay, so let's define those letters again. So F is your final amount. Okay, I is your initial, 1/2 is a constant because we're talking about half-life. Everything cuts down by a half. Okay. T is your time, and H is your half-life. Okay. So that's kind of like how long it takes to decay. Now, one thing I will point out, make sure that these are the same unit. Okay. They should always be the same unit. So whatever you're using, whether it's minutes, hours, days, make sure that you're in the same unit. Okay, so let's read this problem, see if we can set this up and solve this example. So technetium 99 is being used to diagnose brain, thyroid, liver, kidney diseases, and it has a half-life of 6 hours. Great, that's my first key piece of information, right? So I'm going to go ahead and say my H, my half-life is 6 hours. Then we've got 200 milligrams of the substance. That's what we're going to put in. And how much will be left after 6 hours? So wait a minute. I have my initial amount. My I value is going to be 200 mgs. Okay. And the time we're going to look at is 6 hours. All right. And then they actually mention 12 hours and 1 day as well. So I'm just going to list all 3 times. T equals 6, 12, and 24 hours. And we're going to figure out each one of these individually. Okay, so let's set up our equation once. And here we go. We got 200 times 1/2 to the 6 divided by 6 power. And you're going to get 100. So after 6 hours, this is the value. Okay, if we do the same thing with 12 hours, right? We're going to get, instead of 100, we're going to get 50 milligrams left. And finally, let's see what it is after a whole day. And it's the same thing. I'm just changing the time that I'm putting in. And you should get this one to be 12.5 milligrams, okay, after 24 hours. Okay, so 3 calculations we got, and we got 3 different answers. We got after 6 hours, there's 100 milligrams, 12 hours, there's 50 milligrams, and 24 hours, there's now only 12.5 milligrams. In each one, you can see, guys, I just used the same formula and just plugged in a different time for each one to calculate how much there was left at each point. All right, a couple more examples. This is going to be on page 158. And I want you guys to try and set this up and see if you can get the right answer. And you can compare against my work in a minute. All right, so go ahead, pause, try to solve these 2 questions and see if you're getting the same setup and the same answer. So as you can see, I'm back on my compound interest formula. You can see that 22,000 is my initial amount, my principal, a rate of 7.9%, and I'm paying for 5 years compounded monthly. Okay, so I went ahead and plugged in all that information into my equation. Let's see if we got the same result. So after calculating this out, I got $32,614.20, which actually, if you think about it, is kind of crazy, right? That you bought a $22,000 car and you ended up paying $10,000 more than the price of it because you had to take an interest loan on it. Okay, let's do this again. So problem 2, talking about a $500 deposit into an account and waiting 5 years, letting it compound. Okay, so pause, see if you can get the same setup as me, then see if you get the same result at the end. Okay, so here you can see my setup, 500 times 1 plus 0.0325, which is that 3.25%, over 4 times a raised to 4 times 5. And if you crunch out your number, you'll get $587.84. Okay. If you flip ahead to page 159 and look near the bottom, you're going to see a discussion on one other kind of compound interest. And this deals specifically with the situation where we talk about interest that is compounded continuously. Okay, that's the magic word. You never use this formula unless you see the word continuous. Okay, and this formula reads as A equals P times E to the RT power. And some of these letters should be pretty familiar to you. A and P, starting and finishing amounts. E is a new one, okay? Now E, I'm going to note right here, they mentioned, it's a constant. It's kind of like pi, okay? It's not a variable. It's not something that's ever going to change. You're just going to use the same number for it every single time. It's 2.718. Okay, and your calculator has a button for this. Most scientific calculators have an E key, so you should never even have to type this number out. Okay, R is the rate and T is the time. Okay, those two we know and we're pretty familiar with. So let's look at an example of something that grows continuously. Terry deposited $100 that he got for his 5th birthday in a savings account that compounds continuously. Boom. As soon as I see this word continuously, I know I'm talking about these PERT formulas, okay? And it compounds at 5%. Today is his 21st birthday and he wants to withdraw the money. How much money does he have? Well, let's see what we can put together from here. I know that he's starting with $100. So we've got a principal amount of $100. And it's compounding at 5%, so R is 0.05. That's my growth rate. And from his 5th birthday to his 21st birthday, 16 years have gone by. Okay, so I'm going to write it out. 21 minus 5 is 16. But that's how many years have gone by. Okay, let's just plug everything in real quick into this formula and see what it looks like. So his final amount, A, is going to be equal to 100 times E to the 0.05 times 16. All right, and let's punch that in a calculator and see what we get. And when I plugged this in, I got $222.55. Okay, so that $100 after 16 years has a little more than doubled, okay, and gotten to that amount. Okay, so this example comes up after the previous one. Go ahead and see if you can solve this one for compounding continuously. Again, your formula is A equals P times E to the RT power, okay? So again, see if you can solve it and then come compare against my setup. So the first bit is $1,500 invested at 9.5%, compounded continuously for 5 years. And you can see in my setup, I've plugged in the rate, I've plugged in my 5 years and my 1,500. Again, the E is just a constant. It's just going to be a number. And we'll just punch this in our calculator and see what we get. Okay, and I got $2,412.02 after 5 years. Okay, and then it asks us, hey, how much is going to be left in there after 25 years? So one more time, go ahead, pause, solve it, and then see if you get the same answer as me. And for my answer, I got $16,126.52 at the end of that. Okay, so this sums up the unit on compound interest. You can see a lot of different ways we can apply this, whether it's your bank account, how much money you borrow. We can even do this with things that lose value over time. Instead of having a positive percentage as your rate, you would just have a negative percentage. So that wraps up this video. Hope you found it helpful and happy studying.